Investigator, Royal Observatory of Belgium. Professor Dipankar Banerjee, Director, Indian Institute of Science and Technology. Professor T.V. Gopal, Dean, College of Engineering and Technology, SRMIST.
Good morning, all. On behalf of SRM Institute of Science and Technology, one of India's best ranked universities and NAC A++ accredited, we extend a warm welcome to all of you to the Science Working Team meeting of the Project for Onboard Autonomy PROBA-3 mission, jointly organized by European Space Agency, Indian Space Research Organization, Indian Institute of Science and Technology Trivandrum, Center for Atmospheric Science and Climate Studies, Department of Physics and Nanotechnology, and SRM Institute of Science and Technology, Katangultur.
To pay homage to the Tamil language and its rich cultural heritage, Tamil Thai Vartha is sung, and it's an integral part of Tamil culture and tradition. For invocation of the event, let us all rise up for Tamil Thai Vartha.
நீராறும் கடலொடுத்த நிலமடந்தை கிழிலொழுகும் சீராறும் வதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் அதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போலனை துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிளமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Thank you. Lighting the Kuttuvelakku, the lamp, is an old age tradition in India and symbolizes the dispelling of ignorance and ushering in a new chapter filled with purpose and collective auspicious aspirations. May we now request the dignitaries to light the auspicious Kuttuvelakku, the lamp. Thank you all. Thank you, dignitaries. We request our Honorable Vice Chancellor, Professor C. Muttamil Selvan, to facilitate the dignitaries. We may now request Professor Dipankar Banerjee, Director, Indian Institute of Science and Technology, to receive the felicitation on behalf of S. Somnath, Chairman, Indian Space Research Organization, Government of India.
Professor J. Zender, PROBA-3 Project Scientist, ESA. Dr. A. Zuko, Principal Investigator of ASPIICS, Association of Spacecraft for Polarimetric and Imaging Investigation of the Corona of the Sun, Royal Observatory of Belgium. Professor Dipankar Banerjee, Director, Indian Institute of Science and Technology, Trivandrum.
Thank you, sir. Now, we request Professor C. Muttamil Chelvan, Vice Chancellor of SRM Institute of Science and Technology, to deliver the welcome address.
Good morning, esteemed guests, my colleagues, researchers, students, and all gathered here. I take this opportunity to extend a special welcome to Professor Joe, project scientist of the mission ESA, Dr. Andre, ASPIICS Principal Investigator, Royal Observatory of Belgium, and Professor Banerjee from Indian Institute of Space Science and Technology. I also extend a warm welcome to my own colleagues on the dais and the scientists from ESA, students, and all present here. We are extremely happy to host the PROBA-3 Science Working Team meeting at SRM Institute of Science and Technology. I strongly believe that such an event happening in an academic institution will kindle a lot of interest among the faculty and the students to pursue their career in space research. Just to give a brief of SRMIST to the esteemed guests who are here, we are a comprehensive university offering programs in all disciplines like engineering and technology, medicine and health sciences, science and humanities, agriculture, law, management. We are also a multi-campus university, and we have our presence in 6 locations in the country. I can proudly say that we are one of the largest private universities in the country, where 83,000 students have enrolled for their undergraduate program, postgraduate program, and PhD program. It is a comprehensive university. As I said earlier, we have students across India pursuing their higher education here. The Government of India ranks academic institutions every year under the banner National Institutional Ranking Framework. In the NIRF 2024, out of 1180 universities in India, we were placed at the 12th position. And we have been improving our performance and ranking year on year. We are also accredited by international accrediting agents like IET, ABET for some of our engineering programs. We regularly participate in the QS rankings, Times Higher Education and Shanghai ranking, and reasonably perform well in those rankings too. In the year 2009, we wanted to make an attempt to address the global warming and pollution levels in the atmosphere. A group of 50 students and about 5 faculty members formed a team, and they were working on a satellite to be launched. In 2 years, they could develop this satellite with the support of ISRO, and it was launched on October 2011. This mainly to monitor the carbon dioxide and water vapor in the atmosphere. So that was the first attempt SRM made to have some sort of a mission. From then on, lot of interest have been created among the students, and they were working on different projects, of course not to that mega project. Then in the year 2018, we have created Center for Atmospheric Sciences and Climate Studies, where quite a good number of postgraduate students and doctoral students are pursuing their studies. In 2021, we also created a Center for Research, Environment, Sustainability, Advocacy, and Climate Change. So these are some of the things that are related to the event that's happening today. One another thing is, SRM Institute of Science and Technology has been graciously privileged to honor all the chairmen of ISRO since 2008, starting from Dr. Kasturi Rangan to Dr. S. Somanath, with honorary doctorate. This is something very special to us, and for this we remain humble and grateful. In closing, I want to once again welcome each and every one of you to the PROBA-3 Science Working Team meeting. Your presence reflects the shared passion for learning, growth, and collaboration that makes this gathering so special. I strongly believe that your stay is very comfortable in our campus, and I also invite you to visit our campus as and when you find time. With these words, thank you so much for hosting this, for approaching us to host this event at SRM Institute of Science and Technology, and we would like to look forward to more such collaborations. Thank you once again.
Thank you, sir, for welcoming the gathering. Now, may we request Professor Dipankar Banerjee, Director, Indian Institute of Science and Technology, to address the gathering.
Good morning. My present task was to introduce to you today's scheduled chief guest, Dr. S. Somanath. But probably you are all aware that because of changed circumstances, he could not be here in person. In fact, at morning 7 also I tried to reach him out. He was already there in the control room. So he said the countdown has started, so I can't join today. So he was really very keen to come and inaugurate this event. And as Professor Vice Chancellor has told, that there is a long-standing, connect with SRM University, with ISRO. So he was looking forward to come here and spend, half a day here. But unfortunately, because of the changed circumstances, he's not able to do it. But I just, again, on his behalf, I would like to say that how keen he was. And you won't believe it, just as in, just to tell you about, my recent interactions, and his keenness to connect with the public, connect with the academia and industry is phenomenal. In fact, just 2 days back, we were in Guwahati. He had a lot of work at the SHAR, but the minister said that your presence will make a difference. And he flew in to Guwahati, and he met 6,000 students. So he had only come there to interact with the students, and that to school going students. So his commitment to connect with the public at large, and including the academia, the moment we approached him and requested him to inaugurate this session, he immediately agreed on that. So, so I think we see a remarkable change in the approach from ISRO. And also, Sriharikota is now open for public. There are, for every launch occasion, there are 12,000 odd people registering within no time. It gets full in no time. So this openness of the space organization and government's approach is quite phenomenal. So for the youngsters here, I think it's a big change for the possibilities of space program, not only from government sector, from private sector also. I don't know how many of you are aware, within last 2 years, there have been 200 plus startup space companies been registered officially. Today morning, I just got a message from another Hyderabad-based company. They have been given complete clearance of doing any satellite operations from India. So I think for younger people, younger minds here, space is really opening up a completely new avenue. It was somewhat restricted in the past, and also somewhat restricted to the academia and our government agencies only. But for day-to-day, operations and inclusion, space is the next industry domain which you can explore. So, as Professor mentioned, that there is already a tradition of getting involved with the space program. I know that quite a bit of research is happening here in atmospheric sciences, which is again another domain which is very important for our everyday life as well. So, so unfortunately, Dr. Somnath is not here. So anyway, he's a national hero, all of you know. I don't need to really introduce him and his abilities to this Augusta audience, but I would like again take this opportunity to thank SRM, my colleagues, Sanjay, Kiran connected me to Sanjay, and Professor Vice Chancellor has been so supportive. It's unbelievable, because I came only once here for another meeting last year, which Kiran organized, and I was so impressed that this is such a nice place. I also wanted to showcase my European colleagues that how the private universities are coming up in a very big way. And you heard him that this is one of the leading, private academic university within the country. And the numbers are phenomenal. 86,000 students is something which we can't even imagine in other context, or even in our past records of even big government universities. So congratulations, sir, and for your all support. And I thank all of you to be here as well. So we have a changed, completely changed program. We'll be here only up to 11 today. I think some of you are aware. I just want to again reiterate. We are going back to Sriharikota because the launch is scheduled at 4:04 today. And we will reconvene tomorrow, and we'll have a full day session tomorrow. So the students, please join us again tomorrow we'll have scientific sessions, and at the end, we'll also have interaction session with all the scientists, my colleagues who have come from Europe, and also people who are involved in the Aditya project. The idea of this particular meeting was to have a synergy between the PROBA-3 science and Aditya science. So we'll hopefully get back to our drawing board. After the launch, we want the PROBA-3 to the space. So thank you again, and thank you for this opportunity.
Thank you, sir. We now request the dignitaries to occupy the front seats. Now, may we request Dr. A. Zukov, PA of ASPIICS Royal Observatory of Belgium, to introduce Professor J. Zender, PROBA-3 Project Scientist, European Space Agency. We welcome you, sir.
Thank you. Good morning, dear delegates, dear guests, Vice Chancellor. It is really a pleasure to be here, but I will not make the introduction too long, as I'm sure that the delegates are impatient to go to Sriharikota again. Just wanted to say that well, I've been the principal investigator of the PROBA-3 coronagraph for already 11 years, since 2013. And during all these years at ESA, at the European Space Agency, there was a person to whom I could always talk when it was needed, always ask some questions, difficult questions, really difficult questions, and he was always try to help, always try to find the answers. The person whom we used to call simply Joe, Joseph Zender. Please come.
So dear students of the university, I'm very happy to see, or I think we are very happy to see so many of you here. Dear colleagues from Aditya, dear delegates, dear professor, and dear European colleagues, of course. I'm very happy actually to be here and that looking forward to our launch. And wait, give me 1 second. Oh, no, it's okay. It's okay. So I'm very happy to be here. Welcome to everybody. And I hope we will have a wonderful and successful launch. And I would like to give you an overview of the European Space Agency. And I think this is the image why I wanted to have a presentation, right? The rest I probably could do without. But Dr. Sommerta was in the headquarters of ESA this year in March, and he presented to the highest council of ESA. And I don't have to say a lot. Actually, the newspaper said what India is accomplishing in space is astonishing. The European Space Agency director praises ISRO. And I think I was in this room, actually, I was allowed to be there, and it was a really impressive presentation. And I'm sure if Dr. Sommernath would be here, he would give us a wonderful presentation about all the activities in India on space, on the applications, on the commercialization and everything. So unfortunately we missed this, and I'm telling you a little bit now about how ESA is set up and how it works, to give you a very top level overview. Before I start, just to mention, for me it's not the first time in India. The top level image, I couldn't find the group image of the Chandrayaan-1 meeting 19 years ago, when we had the science working team meeting in Bangalore. And then actually it's going for, let me not go, but actually I was regularly back, and I think a lot of the European colleagues could display similar pictures, right? We have a long-standing cooperation with India, and I think we are very happy, and I hope that we can enforce the Aditya PROBA-3 collaboration in the upcoming times. But coming now to ESA, I was thinking about, so how does India compare to ESA? And in the bus yesterday, I asked, how does ISRO work? How is this, right? To understand the differences. So I found on the internet actually a plot. So I think India and Europe have a rather similar size. You have more inhabitants. You have many more languages than we have. But also in Europe, it's you know, we have many countries and many different languages. So ESA is committed for peaceful exploration and the use of space for the benefit of people, society, and planet. And this is very important. This is written in our top-level convention. It's a peaceful exploration. I give you now a setup of where our establishments are, but this is reflecting the structure of the agency. So it's not only where our establishments are, right? Actually, ESA is structured in this way. So we have our headquarters in Paris, in Eswin, in ESA, in Italy. We have the Earth observation. In ESA ESTEC, we have the Technology Center, and actually I'm hosted in ESTEC, and PROBA-3 was built as a technology demonstrator, and the project was in ESTEC. We have in ESOC our Operation Center in Darmstadt in Germany. We have the EAC in Cologne in Germany, which is our Astronaut Center. We have our Astronomy Center in Madrid, ESAC, in Madrid in Spain. We have in EXAT in the UK activities on commercialization and partnerships with industry. We have ESEC as the European Space Security Education Center, but they also operate the PROBA-3 and all the PROBA missions. And then we have our launch facilities in Kourou. So normally we try to launch in Kourou, but I will tell you later that we are very happy that there are other agencies who allow us to give us the opportunity to launch with, for example, with you. Just to give you, I will not talk into the budget, just look at the numbers. Here the explanation is in the difference to India is we are not government funded, right? We get our budget every 5 years approved by a council meeting where all the governments of the member states have to dedicate their budget for 5 years. So that's a little bit different. So we are not funded by the European Union, or right. It's a rather complex activity to get the funding, but we are kind of happy we have a rather stable funding over the years. Now I'm going very quickly in these individual topics, but I'm not spending a lot of time there. Space transportation, you know, we have the Ariane and the Vega. Ariane, we had a delay of the Ariane 6, so our new rocket. We had the maiden launch a few months ago, so this worked reasonably well. Vega, we had an issue 2 years ago with the Vega rocket. It's in Kourou. The launch was foreseen for yesterday. It is delayed again by 24 hours. There was also a hiccup there, but they are sure they can launch tonight. Then we are back and we will have 2 launcher families available for us. Then I would like to go to space safety. Actually, here I will skip the slides. I will just tell you what we are doing there. So the idea is to protect our planet from any outside threats or dangers. So this could be near Earth orbits, asteroids, any near Earth objects. Space weather is part of there. Let me see if I missed one. The space debris, the planetary defense. So for these ones, we have an activity which is run right now at the Operations Center in ISRO with, for example, for the space weather, a mission vigil, which is in the design and development. Earth observation. For Earth observation, there are 3 pillars. The first one is the science, which you see here, the missions around. I don't go into detail. You can read quickly. There is a whole range of scientific interests in scientific fields. So after the science, we do meteorological missions, which is the Meteosat and METOP ones. These are whole families of satellites which are launched one after the other and trying to keep the continuity on the observations so that you can have long-term statistics and everything. And then we have the Sentinels, which are analyzing land, ocean, and the atmosphere. And these are a mixture between, they are not operational, they are more science, but also they are used for operations. It's a mixture. This is, again, a whole family of satellites, and each of the family has, again, a number of satellites which are flown one after the other to keep the continuity. Covering, you see here, land, ocean, land monitoring, ocean forecasting, atmospheric monitoring, and so on. All of this data are in one data pool, which we call the Copernicus Data Space Ecosystem. Just have a look at these numbers in the blobs, right? There is a huge amount of data there. Industry is using this, or institutes, let's say institutes are using the science data. And then industry is using this for weather forecasting and all different kind of applications. Human and robotic exploration, I also want to be rather quick here, because there are several elements. We have, of course, the science in the space environment. We have the space station. We have the European Service Module flying astronauts to the moon with Orion, which is right now in development. We have the Lunar Gateway, so building a lunar post for scientists and for astronauts to do science there. And then we have a lot of opportunities on international mission and commercial landers and so on. On the space station, there will be at one point an end at the space station, and I think it's, I would say it wrong. I will not say a number there, but in a few years, we have regularly astronauts on there. I'll come back to this in a second. So we use the space station quite a lot for scientific investigations. We're looking forward to go to the moon. I mentioned the European Service Module and the Gateway. And the Artemis 2 is planned for to fly the crew to the moon in next year. I hope we can keep the schedule there. To mention ESA astronauts, so on the top you see the astronauts that have flown to the space station. And 2 years ago, we had a call for new astronauts. There were, I think, 20,000 applications coming in. They selected 20 of them. And from the 26 of them are now in the astronaut class. The others are on standby. I think they have finished successfully, this 5 has finished successfully the first year of astronaut training. Navigation, just to mention, we have a Galileo system which offers us our own global positioning system. We have 28 satellites, I thought 22, but 28 satellites and more are launched. And right now the system is complete. We can provide a full service in Europe. Science program and highlights. Here I just want to mention, so this activity is basically where I'm from. I'm in the science department. You will see the solar system explorers, and in the next slide you will see the astronomy missions. And to give you an overview on the low part, this is legacy. So this were all the missions we have been involved and are not active anymore. And you see, for example, we have Chandrayaan-1 in the list because there was a cooperation. Then you see on the top one, we have on the middle one, we have the active ones. So Solar Orbiter, PROBA-2, SOHO, Hinode, IRIS. I think a lot of the scientists know very well. But then we also have Bepi Colombo flying to Mercury. We have JUICE flying to Jupiter. We have Cluster, Mars Express, ExoMars. And then on the top, I hope PROBA-3 will move tomorrow or this afternoon in the middle one. And we have Solar Sea, SMILE, Comet Interceptor, ExoMars, and the Martian Moon exploration. So there are quite a lot of active missions that we are supporting. On the astronomy side, it's very similar. On the low one, you see the legacy. Probably of you will remember Hipparcos, Planck, Herschel, or maybe ISO going back a very long time. We have active, we are involved in the Space Webb Telescope, Euclid, Hubble, Gaia, Cheops, and so on. And then in development, we have Ariel, Roman, Arrakis, Plato, and New Athena. And of course, for the long term, for the gravitational wave studying, we have the LISA spacecraft, which is in development. I'm not sure I'm going to the next slides because let me show you maybe one. Yeah. Oh, wait. Let me show you this one here. These are images observed from Euclid, so they are just a few weeks old. On the lower left part, you see a star cluster, and Euclid is the only spacecraft right now who can see a full star cluster in its full display, but resolving 100,000 of individual stars in there. Another interesting thing, let me see, there was, I think on the top right, and I think it's the yellow spot on a little bit to the left up. This is a galaxy which is the furthest galaxy away we have observed so far. And actually, I would have to look now in my slides in here. It was, I don't find it. It was the oldest one we know. It was very close to the created to the Big Bang. So it's the oldest one we have seen there, or we know up to now. And I think with this one, I would not like to go now in details, and I would like to close. But before I close, I would like to get the delegates again back to stage, because I would like to hand over a few presents to you. So Professor, and please come. Yeah. It's something very small, but I have to carry everything. So here you see the two satellites of PROBA-3. The let's say this is the coronagraph, and this is the occulta spacecraft. So, but you can turn it around to see this. The bunker.
Okay. Thank you so much. Thank you, sir.
Also for you.
Yeah,
that
this is
you-
wonderful. Yeah.
PROBA-3,
Yeah, yeah, thank you. Thank you.
Pancha. I would like actually to get Wolfgang and Werner up here. We have the DARA radiometer. It's a second science instrument on board. And Wolfgang followed this up from the beginning, right? Wolfgang is the principal investigator from the idea to launch. And this afternoon, with the launch, he's handing over, right, when the rocket is lifting at 0, he's handing over to the PI ship to Wolfgang. And I would like to thank both of you, Werner, for everything you have done, and Wolfgang, everything you're going to do, right? And
take the opportunity to thank this long journey. I can tell you, we started planning PROBA-3 in 2005. We had first talks with Philip Lamy and going back. So it's a very long journey that we had. So thank you very much that we reached this day.
okay, thanks a lot. And again, thank you for hosting us here. We appreciate a lot.
No. Good morning, everyone. And I will also start from thanking thanking hosts and Sanjay for taking care of us here and for a great welcome which we received. I'm happy to come back to India. I've been here once already in 2012 for the COSPER Symposium. And now I'm also happy to be in Tamil Nadu. And I learned recently that the Indian Nobel Prize winner Raman was born in Tamil Nadu in Trichy, not too far from here. So I'm happy to be here, and I'm going to make a first science presentation of the day. I will try to make it not too complicated, but well, there will be still an interaction session tomorrow afternoon for students. So if you have questions, if you want to clarify something, you are always welcome to come. So I'm going to talk about Aspics, which is a coronagraph on board PROBA-3. And well, I will start from our way of doing remote sensing observations of the corona. Is there a pointer? Laser. No.
This one you have to.
Yeah, that's all. Yeah. Thank you. So one way to observe the corona is by using EUV images. So this was taken by the telescope on board Solar Dynamics Observatory. But as you can see, we can observe only low corona like this. If we want to observe high corona, then the best way to do is to use an externally occulted coronagraph like LASCO on board SOHO. And you can see that there is a black part here, which we can call the gap, the region where observations are not impossible, but really difficult to make. So we are trying to fill this gap using EUV imagers, so trying to extend the field of view of traditional EUV imagers higher up. So this is what we are doing with the solar orbiter. This is possible. The only problem is that the signal to noise ratio is very quickly degrading because the EUV emission scales as a density square. Density is falling off, and the EUV emission is falling off quickly as well. Why we are not happy with the coronagraph observations of this region? Of course, it is possible. We have internally occulted coronagraphs like Stereo Core 1 or C1 on SOHO. And there are ground-based coronagraphs on Mauna Loa, for example, like what is shown here. The problem with these observations is, of course, the stray light. Stray light in coronagraphs is very difficult to suppress when we are observing the corona below, let's say, 2 solar radii. And in comparison with the wonderful eclipse images, which we can see, well, the images from the internally occulted coronagraphs are not fully satisfactory. So the contrast of small scale features is becoming really low. So the solution which we propose with the PROBA-3 mission is to observe from really down low, like 1.1 essentially up to 3 solar radii, and I'm going to explain you how it is going to happen. So this will be our telescope, which is called Aspics, Association of Spacecraft for Polarimetric and Imaging Investigation of the Corona of the Sun, which will fill this gap and provide another puzzle to the solar terrestrial physics here. So this is, in a sense, an ultimate coronagraph. We are going to launch 2 spacecraft, not 1, but 2. One will carry a circular occulter, and the telescope, we will install it on the second spacecraft. So I put here the updated launch date. We cross the fingers that everything goes fine. So, and of course, the trick is to maintain these 2 together with respect to each other and with respect to the sun. So the distance between the 2 spacecraft is around 144 meters, and the precision of alignment of the 2 spacecraft should be around a few millimeters. So, and this is what we call a formation flying. So the 2 spacecraft are flying as one. This will be maintained over 6 hours in every 20-hour orbit, which is a great improvement in the duration of uninterrupted observations in comparison with a ground-based total solar eclipse, And we will also observe it twice per week on average, which is also an improvement in comparison with the frequency of total solar eclipses, which is, let's say, once per year. So about passbands, I will say later. So we have the spatial resolution around 2.8 arcseconds per pixel. This is our field of view. Nominal synoptic cadence is 60 seconds, but we could go even down to 2 seconds, which would be, I believe, unprecedented for a coronagraph. So it's not actually first time that formation flying, or let's say occultation of the sun by one of the spacecraft has been tried. First time the old mission Apollo-Soyuz, so this was the first docking in space between the two space agencies, so from US and Soviet Union. What was done is that Apollo was occulting the sun, so the sun is actually here. So what you see here mostly are the stray light generated by the protrusions from the Apollo. And Gennady Nikolsky made a certain effort trying to get the coronal intensity. So they observed the F corona, so the dust corona. Why actually we believe that using two spacecraft would be better than just using a single coronagraph? So, the plot here shows the dependence of the stray light, stray light intensity at the center of the entrance pupil with respect to the distance between the external occulter and the entrance pupil. So this is a standard scheme of a LEO coronagraph. So occulter is here and the entrance pupil is here, so the telescope is here. So we are talking about this distance between the occulter and the entrance pupil. And the slanted lines show the same occultation, so how much we occult of the corona. And so we see that the present space coronagraphs are all in the range of, let's say, below 1 meter, the distance between the external occulter and the entrance pupil. And Aspics goes 2 orders of magnitude higher. But you can see that the stray light level in Aspics is actually lower. And we occult to less distance from the solar limb. So the advantage of Aspics is that it allows, in the same time, to decrease the stray light and to approach the field of view to closer to the solar limb. Optical design, I'm not going too much into detail. So the external occulter is not shown here. It's much way this direction. So the entrance pupil, the primary objective, the secondary objective where we have the internal occulter, the second occulter. I will explain a little bit later why we need it. LEO stop, it's a diaphragm, then a few relay lenses and detector here. Why do we need both internal and external occulters? Because the internal occulter is covering the diffraction produced by the external occulter. So if we just have the external occulter, we would have a diffraction ring. If we have only internal occulter, this is much worse, of course. And if we have both external and internal occulters, then the intensity of the diffraction ring is significantly reduced. And we can see that if we are increasing the size of the internal occulter, we are decreasing the stray light. The same way as reducing the size of the LEO stop, we can decrease the stray light. So the LEO stop is covering the diffraction produced by the entrance pupil, entrance aperture. But of course, if we are increasing the size of the internal occulter, we are decreasing the stray light, but we are also pushing away the inner edge of the field of view. So it's a delicate balance between trying to keep the observations useful, really low in the corona, but in the same time to have a stray light low. We have models which would allow to estimate the stray light even in misaligned configurations, as we might expect. Sometimes maybe the alignment of the two spacecraft will not be perfect, but we should be able to calculate the stray light in misaligned configurations and subtract it. In comparison with other coronagraphs, now the rings show the inner fields of view of Stereo Core 2, Vasco, Solar Orbiter Metis at 0.26 AU. So we are covering the gap better than the others. The comparison of the vignetting function. So the perfect vignetting function is, of course, that of the moon. So there is essentially no vignetting. Moon is so far. And our field of view is essentially unminiated, which allows us also to have a good spatial resolution. So in spatial resolution, only METIS, when it's at perihelion, will have the same. 6 filters. So our main passband is the green continuum. So this is the wavelength. This is the irradiance. So the main passband is essentially empty of emission lines. So only for a very hot corona, we will have some weak argon line. And we have 2 narrowband filters. One is iron 14, so the coronal green line, it's here. And here the helium-1 D3. There is no line here because the spectra has been calculated for the corona. So this is the line, the D3 line is produced by prominences. And we have a white light main passband with 3 polarizers oriented at 60 degrees with respect to each other to measure the polarization state of the corona. Scientific objectives. Okay, I'm not going to read you everything. So essentially we are going to address both the physics of quiescent and eruptive corona. Why actually scientifically it's important to have these observations? Well, these are the modeling curves of the acceleration of the solar wind. So from the solar surface to 1 AU, and we see that in the field of view of Aspics, there is a lot of acceleration going on. And also the peak acceleration of coronal mass ejections occurs in the Aspics field of view, well, at least for most of them. A few examples of science cases. So first is, well, we do not measure the coronal magnetic field, but we know that the coronal magnetic field is extremely important for the corona, for structuring, for the dynamics. And currently what we are using are extrapolations, so like what is shown here. So these are photospheric magnetograms, and the extrapolated field is shown here. Well, it's clear from this figure that the extrapolated field is strongly dependent on the model used. So on the left is nonlinear force-free model, on the right is potential field source surface model. And even in the minimum of activity, using exactly the same magnetogram, well, the topology of the magnetic field can be drastically different, like can be seen on this on the west limb here. And of course, even in any case, extrapolated field cannot always reproduce accurately the complex configuration of the magnetic field in the corona. So what we propose to do is, well, of course, what we were trying to do all these years, but now in a different field of view. So to compare the models which can produce synthetic images with future Aspics data, which would allow us to let's say, validate or justify the modeling choices which can be made here. Well, it's clear that this region is very important because there is a crucial transition between the magnetic field dominated corona with closed loops down low and this radial rays where we have the solar wind dominated corona. These are two physical regimes which and the transition between the two is happening exactly in the field of view of Aspics. Origin of the slow solar wind. So this nice cartoon from a paper by Lucia Abba shows the different mechanisms which contribute to slow solar wind. And only 2 of them can be constrained by current observations because our fields of view is not good enough to see all these mechanisms. So essentially, well, one of the main mechanisms is the interchange reconnection. So when the closed field lines are making reconnection with open field lines. Well, open means that they are, well, closing somewhere close to infinity. And in this way, the release of material, release of blobs, which have been observed, could happen. And so this region where this reconnection is happening will be right in the field of view of Aspics. Coronal mass ejections, well, there is quite some discussion in the community about the mechanism. So here I put a comparison between torus instability, so this is ideal MHD instability, which appears for toroidal flux ropes, and magnetic breakout when the magnetic topology is quadrupolar and there can be a reconnection above the erupting flux rope. So it turns out that these models predict different behavior of the coronal magnetic field. So, for example, here in the torus instability, what we have first is the fast eruption onset. So it first snaps open and then the reconnection starts below. Whereas with the breakout, one can argue that this should be other way around. First start the reconnection onset, and then the onset of the fast eruption. So we should be able to, by observing the corona down low, to distinguish between the two, to see, well, of course, we cannot see the magnetic field, but we can see the restructuring of the coronal field, and comparing it with the CME kinematics, with the CME acceleration curves, we should be able to give us a clue about the CME onset and acceleration. And the origin of coronal shock waves, this is, of course, what has been done with radio imaging. So, well, but this figure shows it all. So the type 2 source, type 2 radio burst source is located right in the middle of the gap where we do not have reliable observation. So with Aspics, we will be able to understand what's going on in this region where we have the type 2 emission. Of course, PROBA-3 is not alone there. It will be joining the fleet of other missions. So I here show only two, well, the Solar Orbiter and Parker Solar Probe. The trajectory is shown in red and yellow. We will do stereoscopic coronography with METIS and, well, observe in quadrature the interaction of the corona with this spacecraft. And well, this is the solar cycle projection. So, well, the Parker Solar Probe, Solar Orbiter Aditya L1 has been launched already. PROBA-3 hopefully will be launched today. And Punch is going to be launched at the end of February. So I think an exciting times are coming for coronal science. And we are right in the maximum of solar activity. We have a lot of CMEs. Sounds like great times. And we will even have a total solar eclipse in the August of 2026 to calibrate our observations against the ground-based observations of eclipses. Science operation concept, will not spend too much here. So the duty cycle, which we have, is 6 hours out of 1938 minutes of the orbit. And on average, we do it 2 orbits per week. Orbit is elliptical. So going to 600 kilometers at the perihelion and around 10 Earth radii, perigee, and this is the apogee, and around 10 Earth radii at the apogee. So we will have quite some planning of science operations at the Science Operations Center. So the first periods of observations will be chosen. If we see that there is some active region, we are going to observe it. Okay, and I'm being told that my time is off, so I will show a summary. So PROBA-3 is a perfect example of a mission driven by both science and technology. And due to the unique separation, sorry. Due to the unique separation between the occulter and the telescope, we will be able to see the corona very close in low stray-light conditions, which will allow us to bridge the gap. It will be crucial for solving a few outstanding problems in solar physics. And to finish, I will show you a picture from 2004. There was a defense of a thesis at Marseille, the first PI institution of Aspics, defense by Sébastien Vives. PROBA-3 is there in our minds at least for 20 years already. So this is Jean Arnaud, Philippe Lamy, the first PI of Aspics, who could not be here, unfortunately, Jean-Claude Vial, Serge Couchmy, Jean-Marc Defise. So, all these people have been involved, as you see, from the very beginning. And of course, we should not forget those who are no longer with us. 3 scientists have been deceased since the time we proposed Aspics. So Jean Arnaud from France, died in 2010. Rainer Schwen, who was a great supporter of Aspics, he was the PI of LASCO C1 coronagraph, and Serge Couchmy, who observed his solar eclipses all his life, disease last year. So we thank them all, and we thank you very much for your attention.
Thank you, Professor Zender and Dr. Zukov, for your insightful overview of the European Space Agency and its impactful projects. Again, we thank Professor Zender for your extremely sweet gesture. Thank you very much. Okay.
We have one more talk by Wolfgang to introduce the DARA instrument.
Good morning, everyone. Thank you very much for giving me this opportunity to introduce the DARA instrument on PROBA-3. This is a bit an unexpected situation for me. I was preparing this presentation for the science session of the Science Working Team meeting, so I'm very excited to be here in front of this much bigger and also higher level audience. So I'm a bit, as I said, excited and also a bit nervous, but I'll try to do my best to tell you what DARA is, what DARA can do, what we hope we can do with it, and what science we will try to do with it. So I already mentioned, my name is Wolfgang Finsterle. I'm from the Physikalisch-Meteorologischen Observatorium in Davos in Switzerland. And this is the DARA radiometer, which is installed also on PROBA-3. It is, as a reference, it is about the shoebox size instrument consisting of 2 units. The gold part is the front part, is the radiometer unit with the mirror-plated front face facing the sun. And you see the 3 entrance apertures where which are used to measure the sun. And then the rear part is the control unit, electronics, and power supply, data acquisition, and all the communication. The electronics unit is, the control unit is mounted on the spacecraft, and the radiometer unit is mounted to the front of the spacecraft. So the thermal control is internally made between these 2 units, and we also see a white radiator on the top face of the control unit to get rid of the excess heat. I said it's installed on the PROBA-3. So this is where it is. It's actually on the occulter spacecraft. What you see, this is the occulter spacecraft in the clean room during integration in Belgium. The circular disc with this blue protection wrapping, that's actually the occulter disc for Aspics. And DARA is indicated there. It has the red front protective cover on, which also caused a bit of nervous during the launch campaign, only on my side. So oh, thank you. Thank you. So this is the DARA installed on the occulter spacecraft, and of course it's not protruding above the occulter disc. Okay, this is when we last saw DARA, and I already mentioned this red protective cover made me a bit nervous, because this is the very last photo that we saw from the spacecraft before the payload fairing was closed. And one day before, there was a photo on the ESA blog with all the protective covers and wrappings removed from the spacecraft, but the red cover from DARA was still on. So I was a bit nervous there, but there we can see DARA with the nice shining front plate. So all should be okay. So the front cover was removed on time before the payload fairing was closed. So I was very relieved when I saw this. So how does this radiometer work? This is the core part of the radiometer. It's a sensor head. It consists of 3 radiometric channels. So this is seen from the front. So if you would look, if you would remove the front plate and look into DARA, that's what you would see. So we have 3 light absorbing, these are actually cavities, conical cavities, black coated inside, and also an electrical heater applied to the cones, and thermometers, of course. So these are the electrical connections. And what happens is if the sun illuminates these cavities, the sunlight gets absorbed and the cavity gets hot. And we have this labyrinth structure here that is serving as a heat resistance. So a temperature gradient will build up between the heated cavity and this structure out here, which is, it's all cut from one solid piece of aluminum. So it's no joints that could affect the thermal conductivity. So the temperature gradient will build up through this labyrinth structure, and the temperature gradient is a measure for the heat flux that is flowing from this cavity to the reference block, which is mounted to the front plate actually here. So this is if you would imagine this in 3D. So this is the central part is actually a post sticking out attached to the front shield, which serve as our temperature reference point. So all temperatures of the cavities are measured with respect to the temperature reference point on the front, on the central spot on the front plate of DARA. And why do we need 3 of these channels? It's one is the measuring channel. Then we have a reference channel, and we have a backup channel. And the principle of operation of these radiometers is the electrical substitution principle, which, as I said, we also have electrical heaters on these cavities. So these 2 cavities are closed with a mechanical shutter, so they don't see the sun. This is electrically heated to about 1 degree above the temperature reference point. And then the measuring cavity at the beginning of the cycle is also closed. And the control unit, which sits in the back of the radiometer unit, makes sure that the temperature rise of this cavity is exactly the same as the reference temperature rise in this cavity by adjusting the electrical heater to balance the heat flows from both cavities to the central post. And now what happens if you open the measuring cavity? The controller reduces the electrical heating required because you now also have the solar contribution to the heating. So the optical heating is replacing the electrical heating that was there before. So the difference in the electrical heating between closed and open state is a measure for the total solar heating. That's the measurement principle of these radiometers. And the third cavity, as I said, is the backup cavity. So it serves as a backup, but also to track the degradation of the measuring cavity, because the black coating tends to fade a bit when it's exposed to the sunlight, to the extreme ultraviolet for a longer time. So we open this backup cavity every 2 weeks or so to monitor the degradation of the active cavity. And having the 3 cavities and this full symmetry actually also allows us for redundancy because any of the three cavities can serve as a reference measuring or backup cavity. Okay, so that's the principle of operation. This all needs to be carefully calibrated before launch, obviously. So all the absorptivities, all the entrance aperture areas, all the electronics measurements, the reference voltages. This is a metrology instrument. So we do absolute measurements in SI units, watts per meter square. So this is actually very important. So we need very accurate and careful calibration pre-launch, and we need a means to track the degradation of the accuracy of this unit. Okay, now I want to move on to the science part of my presentation. Total solar irradiance, that's the obvious, the first science objective that we follow with Clara. It's the total solar irradiance is an essential climate variable because it's the input, the energy input to the climate system. By far the dominant energy source for all the climate processes and virtually all processes on planet Earth. So how does this look like? This is a composite of space measurements of the total solar irradiance, which started in the late 1970s, 1978, and it's different experiments in space. They are mentioned here. Stitched together, of course, all degradation corrected, moved, and we've used a machine learning and data fusion algorithm to stitch together these time series from the various experiments to one composite time series. Of course, for climate purposes, it would be interesting to know if if the energy input from the sun into the climate system is changing over the long term. So what we see, what's obviously happening is it changes with the 11-year solar cycle. So this is this 11-year periodicity with an amplitude of about 0.1% on average. Now, for the long-term climate change, it's more interesting to compare the level at the consecutive solar minima. And so far, during the satellite age or satellite era of total solar irradiance measurements, we could not detect any significant change there. So the sun probably did not change in a significant way. And of course, how will it continue? That's where DARA will obviously help to continue this time series that I'm showing here. I mentioned it's important for the climate system. So the Earth radiation budget or Earth energy budget is this. You've probably all seen this picture or similar visualizations of all the radiative processes that occur in the Earth's atmosphere. I took this one from Martin Wild. The numbers are in watts per meter square and taken from different simulations, different models. They're just indicated to show you, to give you an indication of what the spread is of our knowledge, our current knowledge, based knowledge, what we believe it is. So what DARA is contributing is this, the input, and then all these, the output would obviously be the next interesting thing, which I'm going to mention in my next slide. But yeah, so DARA can do this. And now if you remember, and if you looked carefully on the previous slide, the level of TSI is about 1360 watts per meter square. So why is it only 340 here? That's because the averaging over the Earth's surface, which also includes the night side where there's no radiation from the sun hitting the Earth. So you have to divide this by 4. That gives you the 340. So that's where we contribute. And then, of course, the holy grail would be to measure this imbalance, which currently is estimated to be between half a watt per meter square and 1 watt per meter square. So you have to measure each of these quantity very, very accurately in order to be able to really detect this driver of the global warming. We're also trying to do that. And there's different approaches to measure the outgoing radiation. You can use wide field of view or narrow field of view radiometers. There's also the CIRRUS instruments from NASA. They are scanning, narrow field of view, but scanning radiometers. And we have the CLARA instrument. That is a narrow field of view instrument, and it's measuring the Earth outgoing radiation on the night side of the Earth only, so only the thermal emission. So if I go back, so the thermal emission, that's this part that we measure with a very similar radiometer to DARA, but looking down at the Earth and in a narrow field of view. But of course, with the outgoing radiation, it's very important to integrate over the entire surface of the Earth, and it's very inhomogeneous. It's anisotropic. You need to know which scene type you're looking at. So it's not that simple. So there's a lot of calculations, modelings required, and this is just one example of that's the orbit of the CLARA radiometer, which actually flies on this NORSAT-1 mission. And actually the primary payload of NORSAT-1 is a ship tracker, so that's why on this map there's all these the red dots. It's all the cargo ships that are on the ocean. And so this is the foot points of this the footprint of the CLARA radiometer, and then sometimes it's not exactly nadir pointing, so we have to take into account these distortions. So long story short, what we can produce is Earth radiance maps in absolute units, watts per meter square per steradian, and that's such a map produced with the CLARA radiometer. So, oh, okay, I have to speed up. So we are not quite there yet to have a full coverage of the Earth, but we hope we will get there. Yeah, that's an upcoming mission which is also aiming at doing the same, measuring the Earth's radiation budget. I'll skip this because I'm running out of time. I also want to mention the second science objective of DARA. We want to use it for space weather monitoring and to measure the light curves of solar flares. And this has actually been achieved by combining, this is the average light curve of 42 X-class flares observed in TSI. So the flares were identified in X-ray measurements. Then the respective period was taken from TSI, and 42 flares allowed the authors of this paper to actually find this average response or average signature of a flare in TSI. So why would this be interesting at all? Because it's so hardly visible, and flares are clearly visible at other wavelengths. The interesting point here again is we're doing absolute measurements. So we can, this is an energy release curve of the solar flare. which is considered, which is thought to be a very interesting characterization of how a flare works and giving insight to the flare physics. If you know the energy release curve, what we will be able to do with DARA, we will have much higher cadence, so we will have much finer resolution. We will have a very quiet environment along the apogee, where we are not disturbed by eclipses behind the Earth, and maybe, yeah, we will have up to 3-second cadence compared to this. The fastest one in this composite, I believe, was 1 minute, and these are the flares. I just want to show you this very quickly. So the signature of a flare at different wavelengths. H alpha is here also shown as a visible light curve. So we'll probably see something closest to this one. And I mean, if this is that this wiggling is also something that we would be able to see, then that could be, of course, very interesting. And with this, I want to thank you very much for your attention. And because I've been talking about space weather, this is our institute building. And in May, the sky was actually like this because we had the aurora at Davos, 45 degrees northern latitude. So pretty far south for an aurora, but we saw it at our location in Switzerland. Thank you very much.
Well, on the behalf of the whole science team, we would like also to give the gifts to dignitaries. So Vice Chancellor Dipankar, Sanjay, please come here.
I know how good the Belgian chocolate is.
Thank you, Professor Wolfgang. May we now request Dr. Sanjay Kumar Mehta, Associate Professor of Physics and Nanotechnology, to deliver the vote of thanks.
Thank you. So namaste, wanakam, and good morning to all of you. First of all, I thank Professor C. Muthuvachalan, our Honorable Vice Chancellor, giving me opportunity and believing me that I can coordinate this meeting. Thank you, sir. Thank you very much. It is my great pleasure to present the vote of thanks of PROBA-3 Science Working Team meeting. This is one of the important parts of the event. Done as a team to thank and gratitude to each and everyone. All of us has to believe that there are dots which gets connected and then events get created. The first node of this dot was, of course, European Space Agency to contact Professor Dipankar, then Director Aries, and his experience during the National Physics Conclave conducted by Dr. Kiran happened to casually discuss with me that some space scientist and ISRO scientist would like to have the meeting at SRMIST. I was familiar with Aries and ISRO. He suggested my name to him and to European Science Agency. Almost more than 1 month since then the thing was silent, and then Professor George Andar from European European Space Agency sent email mentioning that event to be conducted in last week of November. Knowing it, our Honorable Vice Chancellor immediately called me and said, yes, to go ahead, and asked me to get coordinated from our Dean Research, Professor B. Napoleon, who immensely guided me and proceeded in the right direction. I don't remember then, exactly about 100 emails, conversations taken place between myself and Dr. Andre from the Royal from Belgium. I really thank and appreciate for his patience. The days came closer to the event. Our respected Dean Sciences, Professor John Trudegal, and Head of Department Physics and Nanotechnology, Dr. E. Senthil Kumar, kindly agreed to support the event from the department budget. Thank you, sir. Now, finally, closer to the event, our local organizing committee members, which include our colleagues from Center for Atmospheric Sciences and Climate Studies, Dr. Nagarajas and Dr. Rohit Chakravarti, and colleagues from Physics and Nanotechnology, Professor Malar, Professor Bhatt, Dr. Arjit, Dr. Kiran, Dr. Rohit Dheer, Dr. Devat, and Dr. Jayavardhan, and as well as volunteers and my scholars and several students supported the event. All this work cannot be done without the support from the non-teaching and technical staff working tirelessly to support any need we request. I thank ITKM Communication Department for their support. The support from the SRM Hotel Management was great, and thank them. The Transport Department, especially our GM Transport, Mr. Anand, who helped us to arrange the transport, and also thank media and print to supporting this event. Kindly excuse me if I would have missed anyone. I thank all and wish successful launch of PROBA-3 satellite today. Thank you very much.
Thank you, Professor. Thank you for acknowledging all the efforts and everyone involved. Thank you all. Let us all rise up for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता। पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा। विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा। तव शुभ नामे जागे तव शुभ आशीष मागे। गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे।
Thank you all. May I now request the dignitaries, PROBA-3 working team and SRMIST faculty members to climb the stage for a quick photograph. And I thank all the students, participants for joining the meeting, and you may have your refreshments served outside. Thank you. I request the team to climb the stage for a photograph.